So, we were discussing about power series solutions of second order linear homogeneous equations. Let me give you an example that gives you more insight into the method, into the power series method. So, the example which I am going to do now is which I have already taken, we have earlier in earlier videos. This equation is, so let me give you an example. Example which you already know, that this x into x square x minus 2 y double dash. So, this is what for which you want to find the solutions. Solving this one plus 2 times x minus 1 y dash minus 2 y equal to 0. Okay. So, clearly you can see that. So, you see that x is, because this a naught of x which is 0 at x equal to 0 and x equal to 2. So, you have 0 and 2 are singular points, okay, clearly. So, you divide it. So, this function, this will be p x. So, this is equivalent to y double dash. So, x is in 0 comma 2. So, y double dash plus 2 x minus 1 by x into x minus 2 y dash minus 2 divided by x into x minus 2 y equal to 0. So, clearly these functions, this is p and this is q, these are having power series within this domain 0 2. Okay. So, 0 and 2 are singular points. So, these are the singular points. If you want to solve this equation, so you have to solve, so you pick up some point here. So, let us say 1. So, around 1 if you look for solutions, okay, at x equal to 1 you look for solutions. So, that means you should look for your power series solutions in this fashion. So, y x equal to sigma c n x minus 1 power n. So, this is the power series around the point 1. So, I have x minus 1 instead of x. But this working with this x minus 1 is a little cumbersome. So, let us what we do is, we always, when 1 is the singular, when is the ordinary point around which you, when you look for the solutions like this, you will always shift it, you shift, make, you translate domain. So, that with some transformation, so that 1 becomes 0. So, this becomes 1 and 2 becomes 1. Okay. So, you just shift some transformation, we can do that. So, let us, so what is the transformation? Let z equal to x minus 1. So, at x equal to 1 z is 0. Okay. So, that means what we need, I am going to put I am going to replace the independent variable x with z. So, you have a dy by dx which you have, which you write dy by dz into dz by dx. So, dz by dx is 1. So, you have, these are the same. Similarly, d square y by dx square is simply, so d z of dy by dx which is dy by dz into dz by dx. So, which is again d square y by dz square. Okay. So, you can replace finally z equal to x minus 1. So, you see that x minus 2. So, you replace in terms of z, x is z plus 1. So, z plus 1 into x minus 2, x minus 2 is z minus 1, okay, into d square y by dz square plus 2 times z dy by dz minus 2y equal to 0. Now, z is belongs to, if x is between 0 to 2, z is between minus 1 and it is 2 is 1. So, you have, this is your domain. So, you converted the equation with simple transformation, translation of the independent variable. You can make, now this implies you have minus 1 plus or minus 1 are singular points and 0 is is an ordinary point. Okay. So, I want solutions around 0. So, now this it is not 0 to 1, so it is going to be minus 1 to 1. I translated. Now 0 is so plus or minus 1 are singular points. 0 is an ordinary point. So, you can look for solutions for this equation now. Okay. So, we have already seen earlier that this equation has a solution, one solution, which is y1 of x. If you actually see one solution is 1 minus x. This is one solution. So, and then you can find your other solution once you know one solution. Okay. From the Abel's formula you can get your y2x. So, x minus 1 is your z, and that means the corresponding equation will have this equation. So, already you have y1 of z, one solution is minus z, okay, because it is a homogeneous equation, minus z or plus z. So, if you can substitute inside there, so dy1 by dz and d square y1 by dz square. So, that is 0. So, this part will not contribute. So, we will have, you can see that this is the solution just by looking at 2z, dy by dz is minus 1 minus 2 times y is plus z, minus z. So, it is going to be plus. Okay. So, because it is a homogeneous solution, any constant multiple of y1 is also a solution, you need not worry about this minus. You can multiply with minus 1 into minus z, that is plus z, that is the solution. So, if you use that, you have 2z 1 minus 2 times z, so that is 0. So, it is satisfying. So, this is one solution. Okay. If this is one solution, what is your other solution by the Abel's formula? So, the method 1 is this. Method 1 is, so this is and z is y1 is z, and z is between minus 1 to 1. Within this you have the solution. Now, y to z you can similarly you can calculate. Y to z is actually so the formula is you can look into the Abel's formula. So, that is so y1. So, y1 into integral x naught to x. So, we have instead of x we have z. Okay. So, y to z simply you have minus e power minus integral px dx. Okay, let me write now what we have now. So, y to z is y1 z times integral 1 by y1 square into e power minus integral, what is your p? P is 2z divided by z plus 1 into z minus 1 dz. Afterwards you have a dz. So, you can fix it from z naught to z and make this z as the dummy variable inside, but because 0 is part of the domain, so you can do that. So, you can you choose z naught belongs to 0. So, you can also do this 0 to z. Okay. So, and this becomes some t square. So, you have make it dt, this is some ds. So, s minus 1, s plus 1 and 2s. This is also from 0 to t. So, we want function of t. Okay. So, this you can actually calculate and see some expression. Okay. So, I have done it. So, I see that it is actually, I can write it directly. So, you can evaluate this by partial fractions. You first calculate this, you evaluate this integral first, and then exponential of that, and 1 divided by t square, okay, and then you integrate. So, you finally get, so you can write z times or 1 minus z times log square root of z plus 1 modulus of this, okay, and then 2 minus x is 1 plus 1 minus x, 1 minus z, this is 1 minus z, 1 minus z. So, we have, so you simply write z square minus 1 or 1 minus z square. So, modulus of this, you need not write modulus because your z is between minus 1 to 1, and 1 minus z square is always positive. So, this is what you will get if you actually calculate. Okay. So, this is your second solution. Once you get these two, you can see that z is one solution and y 2 is 1 minus z times, so both are two linearly independent solutions. So, you can write the general solution y x as c 1 z plus c 1 of sorry, this is not x, this is z, z c 1 z plus c 2 times 1 minus z log square root of 1 minus z square. So, this is what you have as a general solution. So, this implies you can go back to new variables as y of y 1 of x as a general solution. In terms of x, you can write c 1 times what you have is z is x minus 1. So, c 1 x minus 1 plus c 2 1 minus z is x minus 1 minus z square, okay, right, that is what you have. So, for example, x is z plus 1 and then 2 minus x is 1 plus 1 minus x, that is 2 minus x, so 1 minus z. So, we have z square or 1 minus z square, 1 minus z square. So, this is what we have, correct. C 2 times 1 minus z, z is x minus 1 z times log square root of 1 minus z square, z is x minus 1 square. So, that is 1 minus x square plus 2 x minus 1. So, you have x times 2 minus x, so which is positive. So, this is what is your now x is in the domain between 0 to 2. So, I simply translate it from z to x. This is what is your general solution. Okay. So, what happens if you look at the power series solution to the same equation, you may end up getting one solution may be same, or the other solution you may get a series solution, but that need not be expression for the y 2 you get here, because these two are linearly independent solutions. Okay. I will simply give you an example. 1 and x are two linearly independent solutions of some equation, let us say. So, then 1 plus x and 1 minus x, these are also solutions of that homogeneous equations and they are also linearly independent. So, what you get from your power series solutions, you may get your power series solutions, let me call it y 1 x, y 2 x for the same equation. For some differential equation, these are the solutions, okay, and these are two linearly independent solutions. Now, these are also 1 plus x, 1 minus x are also solutions, because 1 and x are solutions of a homogeneous equation, their summation is also or difference is also solution, and these are also two linearly independent solutions, this one and this one, okay, both together. So, when you are given a second order equation, by the power series method, when you derive the solutions y 1 and y 2, when you determine the solutions y 1 and y 2, you do not know exactly. So, sometimes when it is matching directly, you may see that I may get x minus 1 or 1 minus x. Okay. What is your solution? First solution what you got is 1 minus x. You may see that first solution may be 1 minus x. Second solution you are not sure, it may be the combination of y 1 plus y 2 as a series. Okay. So, you do not know exactly, see y 1 y 2 is actually 1 minus x minus 1 log square root of x into 2 minus x. So, the series solution which you may get, this need not be exactly this is not the expression for the solution which you already derived for y 2. Okay. So, y 2 here is 1 minus x minus 1 log square root of x into 2 minus x, and what you got from the power series means you have two linearly independent solutions. You do not know whether they are from this or this, okay, or need not be this I can take this and 1 minus x, these are also two linearly independent solutions. Okay. I have two linearly independent solutions here also. Okay. So, you do not know. So, it may match, one I may match, a second one, even though it is some series power series solution, that need not be exactly what you have, okay, earlier. So, in this case 1 minus x minus 1 log square root of x into 2 minus x. So, let us use that method, power series method, we will apply power series method to find the solution for this equation. So, this is the equation we will look at it right now in terms of z. So, that 0 is the ordinary point. So, we will see the method 2 as a power series method. Let us look at the method 2 as a power series method. So, method 2, what we have is, we look for let so y of z, you look for as a power series, n is from 0 to infinity C n z power n. Okay. What is z? Z is between minus 1 to 1. Because this p x and q x, okay, so this q x 2z divided by this and minus 2 divided by this, they have power series which is converging in between minus 1 to 1, and your power series here also you can expect to be between minus 1 to 1, they are converging uniformly. Okay. So, that you can differentiate term by term. So, dy by dz you can calculate, and d square y by dz square you can calculate. So, I will just write directly write. So, you have z plus 1 z minus 1. So, z square minus 1, okay, into d square y by dz square. So, which I write n is from 2 to infinity n into n minus 1 C n z power n minus 2. Okay. So, this is what you will get as a solution as a two derivatives of y, plus 2 times, that is what we have, plus 2 z dy by dz, plus 2 z dy by dz is n is from 1 to infinity n C n z power n minus 1 minus 2 y. 2 y is simply C n z power n, n is from 0 to infinity equal to 0. This is what happened when you substitute your power series solution into the equation. So, you can rewrite this implies z square into this one. So, we can write n is from 2 to infinity n into n minus 1 C n z power n. If I multiply, that is the first term, I expand this z square into this and minus 1 into this. So, I have minus sigma n is from 2 to infinity n into n minus 1 C n z power n minus 2 plus 2 sigma n is from 1 to infinity n C n. So, you can write 2 inside 2 n C n z power n minus 2 sigma here also n is 0 to infinity 2 C n z power n, which is equal to 0. You see that all the powers are z power n except here. Okay. So, this you can convert it, you can make equivalent. So, just by changing the index, if I replace, if I want z power n by 2 z power n minus 2, I have to replace n by n plus 2. Okay. If I replace n by n plus 2, what happens to this? This is actually equal to n equal to n plus 2 equal to 2 to infinity. In the place of n plus 2, in the place of n plus 2 minus 1. So, n plus 1 and then C n plus 2 z power n plus 2 minus 2 is z power n. So, this is what you have. So, n plus 2 equal to 2 to cancel. So, what you have is simply n is running from 0 to infinity. This is what you can replace with this. Okay. So, I am replacing finally n is from 0 to infinity n plus 1 n plus 2 C n plus 2 z power n. Okay. Now, I replaced. So, this is how you change the index. You want that second term, so which is z power n minus 2, which you can convert just replacing n equal to n plus 2. Now, you see that all the powers are z power n. So, what are the isolated terms? This is running from 2 to infinity, from 0 to infinity, 1 to infinity, this is from 0 to infinity. So, the isolated terms are 0, 1. Okay. So, those terms you can write outside. If you write that outside, n equal to 0 here. So, this is n equal to 2 onwards, you can write it is common, okay, n into n plus n minus 1 C n plus 2 n here, okay, and you have minus 2 n minus 2 C n. So, this is what you have into C n z power n. So, n is from 2 to infinity, I picked it from these 3 sums. Okay. When I write that, and this I write as it is, n is from here also 2 to infinity, I write n plus 1 n plus 2 C n plus 2 z power n. So, what is left when I picked up n equal to 2 here. So, 2 to infinity finished everything. Here I wrote 2 to infinity, I already added here, but 1 I did not write. So, 1 n equal to 1, you have 2 C 1 z. Okay. So, now this term has everything. So, here minus 2 n equal to 0, 2 C 0 z power 0 minus 2 C 1 z. Okay. And here n equal to 0. In this power series, I wrote only 2 to infinity. So, I have a minus n equal to 0, you have 2 C 2 z power 0 is 1, and then n equal to 1 minus n equal to 1 is 2 3 6 C 3 into z, okay, which is equal to 0. Okay. This implies you have this. Now, what happens? This you have a left hand side is the power series. So, you can combine these two series because z power n, it is running also from 2 to infinity, n is from 2 to infinity, both is common. So, you have you can n square n into n plus 1 n minus 1 plus 2 n minus 2. What is this one? So, this is actually n minus 1 is common. What you have is n plus 2. Okay. This is what you have. So, n minus 1 n plus 2 is this term. So, into C n z power n. So, minus n plus 1 into n plus 2 into C n plus 2. So, n plus 2 is also common both places, both sides n plus 2 is common. So, I removed here, I removed here. So, you have C n minus n plus 1 C n plus 2 into z power n. Okay, this is both the series I combined. Now, if I can write all 2 C naught minus 2 C naught plus C 2 together, and this what about z? Z is 2 C 1 z, 2 C 1 z cancels. What you have is minus 6 C 3 z equal to. Okay. So, right side is a series power series with 0 power series. So, you can coefficient of z power 0, z power 1, z all other terms n equal to 2 to infinity, you can make it coefficients, you can make it 0. So, that gives me, so z power 0 coefficient of z power 0 is actually 0, coefficient of z power 1 0. So, this will give me coefficient of z power 0 will give me C 0 or C 2 is minus C 0, okay, and this will give me C 3 as 0. Now, coefficient of z square is n equal to 2. Okay. So, n equal to 2, what you get is n equal to 2, if you substitute this has to be 0 by putting n equal to 2. So, okay. So, n equal to 2 is simply C 2 minus 3 C 4 is 0. Now, C 3 is 0 implies C 4 is also 0. Okay. Sorry, C 2 is C 4 is C 4 is equal to C 2 by 3. C 2 by 3 is minus C 0 by 3. that is what is your C4. N equal to 3, you get the same thing. So, this will give me 2Cn, 2Cn C3 minus n equal to 3, 4C5 equal to 0. So, this will give me, because C3 is 0, C5 is 0. Okay. Like that you can get n equal to 4, n equal to 4 you will get again n equal to 4, if you do, you will get 3C4 minus 5C6 equal to 0. So, this will give me C6, if you write as 3C4 by 5, that will give me minus C0 by 5 again, because C4 is minus C0 by 3, 3 cancels. So, that is what you get. So, n equal to 5 also you do it. So, this will give me n equal to 5 is C5, because C5 is 0, C7 is also 0. So, you will get C7 0. N equal to 6 will give me C8, again you can see that is going to be C0 by 7, like this you will get. So, what is your solution? I could get all most of the coefficients except 1 or 2. Okay. So, you see that I could write C2 in terms of C0, C3, C4, C0. So, C0, C1 I could not get it. So, what is your solution? YZ is C0 plus C1Z and so on. So, C0 I could not find, plus C1 I could not find. Okay. Yes, I found, right. So, what is C1? C1 is, I could not find C1, and then C2, C2 is minus C0 into Z square, and then C3 0, C4, C4 is a minus, C4 is minus C0 3, C0 by 3, C4. So, this you have Z power 4, C5 is 0, C6 is again minus C0 by 5, Z power 6, C7 0, again C8 is minus C0 by 7, Z power 8, and so on. So, what is this one? This is actually equal to C1Z plus C0 into 1 plus 1 minus Z square, okay, minus Z power 4 by 3 minus Z power 6 by 5 minus Z power 8 by 7, and so on. So, if you rewrite, so this is actually y of z is C1 of z plus C0 1 minus z times, this is, you can rewrite z minus plus z cube by 3, z power plus power 5 by 5, z plus 7 by 7, and so on. So, this is what you have. So, if I choose, these two are arbitrary constant now. If C1 equal to 1 and C0 is 0, in the power series method you get your y1 of z as z. This is exactly, this is matching with my earlier method. Okay. You can see that y1z is my z. Okay. I got the same solution even here by the power series method. Z is between minus 1 to 1. Okay. That is the area in which I am working. So, what is your y2? So, you get C1 is 0, C0 equal to 1 if you choose, then you get your second solution, second two linearly independent solution, that is 1 minus z times this power series. This power series is what n is from 0 to n is from 0 to infinity, z power 2n plus 1, okay, divided by 2n plus 1. This is what is the series, right. So, if you can recognize this series, n equal to 0 z, right. So, n equal to 1, n equal to 1 is 3, z 3 by 3, n equal to 2 is 5 by 5, and so on, okay. 5, 7, 9 and so on you will get. So, this is the series you will get. So, but you are not sure, but this is, I am not saying, I am not claiming that this y to z is exactly the form what you got for here. This is not your y2, okay. This is not exactly, or this is the one, this is your y2. If you see this your y2 solution, y2 is this. I am not saying this what you got is the expression for the same so this power series is not the representation for this y2. This y2 could be linear combination of this and z and this together, you do not know exactly, or linear combination of z and this y2 could be that expression for y2. Okay. So, in any case you got, if you can recognize this, this is another linearly independent solution. So, this is how you get a linearly independent solution. So, finally, y z is some C0, or if you want to use the same C1, I will use the C1 or D1, linear combination of arbitrary constant D1 into Z plus D2 into 1 minus Z, this power series. This actually converges to 2n plus 1 by 2n plus 1. This power series, this converges for every z between minus 1 to 1. It's converging absolutely and uniformly within this domain. Okay. So, this power series. Okay. So, you have, this is the general solution, this is the general solution in z. Okay. That is why z is between minus 1 to 1. You can also write in terms of x, we know already. So, d1 z is, what is your z? Z you have chosen as, z is the transformation with x equal x minus 1. So, in terms of x, if you want original equation, x minus 1 plus d2. So, 1 minus x minus 1, and this sigma n is from 0 to infinity, x minus 1 power 2n plus 1 by 2n plus 1. So, this is your thing, and now x is between 0 to 2. So, this is what you have. Okay. And in the method 1, what you calculated is this, even though it is valid between, you can see that this y2 is actually valid here, but the way you calculate it here. So, I took the domain from 0 to z dt, here in the, while calculating the Abel's formula, I assume that t is not equal to 0. Okay. So, you can, so y1 I cannot, so because I divide this y1 1 by y1 of t square. So, when you are doing it, 0 should not be part of the domain. Okay. 0 should not be part of the domain. So, otherwise integral 1 by t square, you have t at t equal to 0, you will have a problem. Okay. So, if you actually do without this, it is not definite integration. If you do not do the indefinite integration, if you do, you have simply d square dz. You do everything as a definite indefinite integration, this, so that you have z plus 1 z minus 1 into dz. Okay. If you do this, this is what you get, because you are dividing with 1 by z square. Z is, you are not supposed, you are not assuming that 0 is not part of your domain, that is what I explained earlier, minus 1 to 1. So, you assume that between minus 1 to 0, you calculate this expression, that is what I get. Okay. And also between, assume that 0 to 1, you calculate the same expression, again you will get the same. Okay. If you want to do the indefinite integration, your domain is this. So, you pick up some say some half or any x naught. Okay. Your z naught you should pick up as some quantity in between in your domain. So, that you can do, because I do not want, because 0 is not part of the domain. So, I do not want to use the indefinite integration from z naught to z. Okay. Instead, so that I have to pick up my z naught from the domain minus 1 to 0. Okay. So, which I avoided by doing indefinite integration. Okay. Which is also valid only in this domain. You calculate it, this is what you get. Again you do the same thing, thinking that your domain is only this, 0 is not part of the domain. Okay. So, this is what you get, which is valid actually between minus 1 to 0 and 0 1. What happens at 0? At 0 is also there is no issue, that is a solution, because because the method only is actually giving you, allowing you to find the solution this here once and here as the same expression. So, it should, because it is continuous, 0 is also is not an issue. So, that you have a z which is between -1 to 1. Actually, in the method 1 which you used Abel's formula, in that y1 should not be 0. So, 0 is not part of the domain, okay. But 0 as such, there is no issue with the 0, z is 0 is an ordinary point. So, actually it is not a issue, it is not an issue with the differential equation. That is why in the power series method you worked with the solution directly, you directly have between -1 to 1, there is no domain breaking here. So, you are not breaking into -1 to 0 and 0 to 1 as in the Abel's formula, okay. In this power series method you directly get, you do not have problem with the z equal to 0, okay. In both the cases anyway, so you got the same expression. So, you have an expression, you have two linearly independent solutions in both the cases, that will be the general solution, okay. So, this will give, I hope this gives you an insight about the power series method. Next video we will apply the power series method to the second order equation, the special second order linear homogeneous equation which comes in the applications. It is called Legendre equations, okay. Legendre's differential equation, I will solve the Legendre equation with the power series method, okay. That we will see in the next video.